Okay, with our first one here, how can we make this a little bit easier and nicer for us?
Oh, sorry.
You don't want to do this? Alright, while I finagle with this more, what can we do to make it a little bit nicer? Combine radicals? What do you mean by that?
Like, put everything, well, not everything, but so x cubed minus 1 to 1/2, to 1/2.
Alright, so rewrite it like this, x cubed minus 1 to the 1/2, to the 1/2. Alright, what can we do with that? Multiply what? Exponents, good. So our exponent rules say that we can, when we have a power raised to power, just multiply it together. And we have then x cubed minus 1 to the 1/4. Square root of square root is the 4th root. Okay, so that's my y function. Is that a lot easier to take? It is. Alright, so now let's go ahead and find our derivative. And did we get 1/4 x cubed minus 1 to the negative 3/4 times 3x squared? Do we agree? Now, chain rule, like we saw from last class, really isn't that bad. It's just the thing that most people mess up is forgetting to multiply by the derivative of the inside, the chain part. Alright, so make sure to do that. Got any questions on one? Yeah, for each response we can leave it like this. If it's multiple choice, leave it simplified. Alright, other questions? Okay, number 2. So find y prime, y double prime, y triple prime. We said this y prime is our first derivative. Our y double prime is our second derivative, which means the derivative of the derivative. And y triple prime is our third derivative. Okay, so we need to first start off by finding our first derivative. What is my first derivative? 7. Good, inside stays the same. The 6. That's 2. Let's go ahead and simplify that. It's going to be easier to find later derivatives. Higher order derivatives is what we call them. If we go ahead and simplify. 3 raised to the 6th. Alright, so that was my y prime. So that's 1 of x. Alright, now y double prime. What do we get for that? I think I heard 84. 84 times
2x minus 3.
Times 2. See, especially when you're doing so much in the beginning, it's easy to forget about that last part there. Alright, let's just go and simplify that. 84 times 2? 168. 2x minus 3. Alright, that's my second derivative. Now my third derivative, what do we get? 8.
840.
Oh, 840. So 5 times 168, right? Is that 840? 2x minus 3 raised to the 4th and 2 times 2. Now, again, for response, we can leave it like this. Questions on that? What do you think the 28th derivative would be? Or 0, something over, and a lot of staring. What do we think about it? What's happening with each of our powers as we move on? They're dropping down, right? And then, yeah, we're getting bigger and bigger numbers here. Eventually, my power is going to drop down to what? Negatives, that's true. I didn't think about that. Whoops. Whoops. Yeah, it's going to drop to negative. Okay, well, I was trying to get something else there. Let me ask you this. Say that our third derivative was this. What will be your 28th derivative, do you think? 0, you guys are catching it. Okay, So if I continue to take the derivative over and 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 over here, think about it. If I have y equals 5, let's just go basic. Alright, what is y prime of this guy? 10x. What is y double prime of this? 10. What is y triple prime of this? 0. See, do I go into the negatives with this guy? Nope. So think about this one then. At some point, we're going to have big number times 2x minus 3 to what power there? If I keep dropping in power, what does my power eventually become? 0 times some numbers. Right? Now, what is anything to the 0 power? 1. We'll look at, so if I have them here, so like look over here, we're dropping it in power each time, and eventually we're going to get where we don't have a variable anymore, right? So here my power is 1, so here technically I have x to the 0th power. I have no variable anymore. Same idea. Does that make sense? Also, guys, if we think about it this way, if I were to actually multiply this craziness out, if I were to multiply this out, what would be my largest power if I were to multiply that out? X to the 4th. So some crazy number, x to the 4th plus some other stuff, x cubed plus some other stuff, x squared, so on and so forth, right? And eventually, since I'm going to a pretty high power here, eventually this is going to become some number times x to the 0th, or really just some number, right? Likewise here, this is going to eventually become some number. Eventually this will become some number. And as we go through and take the derivative, we know the derivative of these constants ends up being 0. Now we're going to start losing some of them before others, right? This is going to hit my constant and thus 0 before this guy does, which does before this guy. Does that make sense what we're saying there? So you can think that kind of with my polynomials, like starting off with this, my parabola was my original and a line, and my line has the same slope all the way around, so then that's a constant, and the slope of a constant is just 0. That's just thinking questions. Questions on that, though, I know if there's something really weird at you. Good. Okay. I think that's all I want to do. Okay. So today what we're going to be talking about is... Oh, wait. No, we need to go over your homework. Let's go over your homework, guys. Chain rule. I know we've already talked about what differentiability is in general. But today we're going to be looking specifically at polynomial functions. And if we get a chance, we're also going to look at piecewise functions. Reminder, MHS interest meeting tomorrow after school in the lecture hall. If you missed the first one and you want to come. Okay. So again, let's talk about what it means to have a limit exist, what it means to be continuous at a point, what it means to be differentiable at a point. Because again, these are huge concepts. Alright, so let's first remember for a limit to exist, we'll talk about continuity. Continuous. And differentiable. Alright, so we know for my limit to exist, I must have that left-hand limit and the right-hand limit equal each other. Right? So I must have my limit as x approaches some value from the left must equal the limit as x approaches that same value from the right. So my left hand and my right hand must be equal in order for me to say that the overall limit exists. And we keep saying it, and I'll keep saying it again. We don't have to have the function defined there, right? We don't have to have f of c. We might have it, we might not. All right, for continuous, we had 3 conditions. First, f of c must be defined, meaning it equals some number. We actually have that point on our graph. And secondly, we have to go back to visiting our limit world. And the limit as x approaches c of my function must also exist. And we know that that sub heading means that we're going to have to meet these 2 requirements, a left and right hand being equal. And then third, in order for our function to be continuous at a point, so we're looking at x equal to c, we must have that the function value is actually equal to that limit. Then we can say that f of x is continuous at x equals c. Okay, now differentiable we talked about as well. Differentiable, we said that we cannot have the corner, cusp, vertical, tangent, or discontinuity. The general thing that we said was that our slope from the right, so our limit as x approaches c, sorry, let's go left first, of my derivative must equal the slope on the left, must equal the slope on the right. So x approaches c from the right of my derivative. Okay, so in other words, slope coming from the left must equal the slope coming from the right. We'll say this is c. Okay. Now, we talked about also that if a function is differentiable, then that means that it is continuous. Now, likewise with that, I want to throw something else in here. It's kind of an extension of the differentiability. Alright, so if a function is differentiable, then that means that your original function is continuous. And you must also have your derivative is continuous. If I have my original function is continuous and my derivative is continuous, that's another way that I can know my original function is differentiable. And if we just say differentiable, we mean differentiable everywhere, right? So, which that makes sense because in order for the derivative to exist at that particular point, so differentiable, again, we're talking about specifically at a point C. When we're looking at the slope coming from the left, going towards C, and the slope going to the right of C. If those are the same, then we can say it's differentiable at C, meaning we can take the derivative at C. If it's not differentiable, then we don't have the derivative there. Right? Now, if a function is just differentiable in general, that means it's differentiable everywhere. Then from there, we can say that the original function itself is continuous, which we had to have it be continuous or be differentiable. And likewise, the derivative is continuous, which makes sense because if it's differentiable everywhere, that means the derivative exists everywhere. My left hand and right hand must equal each other everywhere, and it exists everywhere, then we have it to be continuous. Okay, so again, the difference is between. Now, the other big thing we talked about, the huge takeaway. Let's go. Alright, so remember, all differentiable functions are continuous. All differentiable functions are continuous. We talked about that there. If a function is differentiable, then that means that it is continuous. Okay, so in geometry, logic, notation, PQ, if-then statements, we had that differentiability implied continuity. And we talked about, can we go the other way? If it is continuous, does it mean it's differentiable? No. So be careful not I feel like I should check in and make sure everyone's like alive and there's not. Should we be in a lockdown right now? All right. So not all continuous functions are differentiable. Okay, so we know differentiability implies continuity. You'll hear me say that over and over and over again. Differentiability implies continuity, but doesn't necessarily go the other way around. Okay, so I think a quick and easy example to think of for this is if we consider the absolute value function. So consider y equal to the absolute value of x. Is this continuous everywhere? Yeah, that's continuous everywhere. Is it differentiable everywhere? Now, where's my issue of differentiability? Okay, so here we have it's continuous, but big time not differentiable. And specifically, and again, what we mean is continuous everywhere, but not differentiable everywhere, or differentiable everywhere, but x equals 0. All right. So let's use all that. All right, show that. Some great words in calculus. Show that y equals the cube root of x is continuous, but not differentiable What point do you guys think I'm going to make? Any thoughts? Or is it not differentiable? 0. All right, so show that this function is continuous, but not differentiable at 0. All right, so first let's show the continuity. All right, so continuity we know we have to first have the function is defined. We've got 3 things for continuity. First, what is y equal to at x equal to 0? Actually, we should specify where we are first because it's not y of x, so at x equal to 0, what is y? 0. All right, sweet. We're well on our way there. All right, next let's take a look at the limit. So the limit as x approaches 0 of my function, so of y, just get rid of x. What is that equal to? 0. How could we do that so quickly? Just direct substitution, right? Always try direct substitution first. Can I plug it in? What's the cube root of 0? 0. Ooh, that looks good for us. Third requirement, they must equal each other. So at x equal to 0, y equals 0. I don't like that it's a y. F of x is just so much nicer because we'd say f of 0 is 0. But that's okay. Technically, what you guys can do on an AP exam, if you have this for free response, you can say let f of x equal y, which equals that, and then you can just use f of x. But it's not necessary. All right. So x equals 0, y equals 0, which equals the limit as x approaches 0 of y. Boom. So now we can say y is continuous at x equal to 0. We good there? Okay, so we showed the continuity. All right. but supposedly it's not differentiable there. If we think of our graph, what does it look like? A snake? That was a pretty good one. If we think of our graph, what does the derivative look like at that point? That vertical line, good. So we know it's not differentiable because that tangent is vertical. Now, graphs are not justification. They help us to see, but they are not sufficient for showing, proving, yada yada. So we've got to show that. All right. I don't remember if I made you write this last time or not. Did we talk about another way to write derivative left-hand, right-hand notation? Okay, let's squeeze it in here. Another way that we can write, so here we talk about basically the derivative from the left, the slope from the left, the derivative from the right, the slope from the right. Another notation for this, just right here, is I could have said f prime of x, that means from the left, and f prime of x, the little plus sign means from the right. So that's saying the derivative from the left or from the right. Now, x would have to be some actual number, right? So actually, I should probably say like f prime of c to indicate that it's an actual number and not a variable. So this means left-hand derivative, so that slope as we come from the left. Right-hand derivative slope as we come from the right. Okay, that's just some different notation. Okay, so now let's take a look at our derivative. Hey, don't we know how to do derivatives now? Yes, right? Some of them? Okay. Can we take the derivative of this guy? Yeah. Okay, so let's go ahead and take our derivative. Y equals x to the 1/3. All right. So what is y prime going to be? 1/3 x to the negative 2/3. Do we agree with that? Okay, so we're taking our derivative, which is great, this is our derivative, but is my derivative defined at 0? Well, let's take a look at what this means. What's another way I can write this? 3x to the 2/3. All right, so this is my derivative. From just my derivative equation, I should be able to see, is it defined at 0? No, no. In fact, if we try to put in 0, so at 0, at x equals 0, y prime equals 1/0, which is undefined, right? So here we have, it was continuous, but y is not differentiable, meaning the derivative does not exist, it's not defined. Differentiable means we can take the derivative, non-differentiable means, or not differentiable means we can't. It's not differentiable at x equals 0. Before we had to consider the graph, or we would have to consider that limit from the left, limit from the right. We still could have done that. We could have set it up and said, what is my limit from the left, limit from the right? But now that we can actually take the derivative, we can actually just look to see, what are my restrictions on my derivative? So here we have a case, is my derivative continuous? Is this function continuous everywhere? No, what's my area of discontinuity? 0. And what kind of discontinuity is that? Yeah, it ends up being an asymptote, right? Makes that denominator 0. So we have then is that our derivative ends up having an asymptote at 0. So my derivative is not continuous, which means it is not differentiable somewhere. So it's not differentiable everywhere. Okay. So if I can find this area where my derivative is not continuous, that means it's not differentiable, because it has to be continuous in order to be different. Questions on that? Okay. So let's do a similar thing, but with my absolute value. So let's consider y equals the absolute value of x. And again, show that y is continuous, but not differentiable at x equals 0. And this will help us kind of look into piecewise functions. Actually, that y is continuous, but not differentiable at x equals 0. All right, let's start off with their continuity. All right, so we're investigating at x equals 0. What is y equal? 0. Good, great. It's defined. First condition met. All right, my second condition of continuity. What do I need to check? The limits. Good. Left hand and right hand limit. All right. So let's see. The limit as x approaches 0 of f of x. You can think of your graph for this. Now again, we're talking about limits here. So remember, limit is just what is the value approaching. What's my value approaching from the left and the right? 0. That's great. My limit is 0. Looky there. So we have x equals 0, y equals 0, which is the same as my limit. So the function's continuous. I'm going to trust he has it under control. If they start banging on the walls, then we'll have to. Okay, and we're specifying right at 0. I kind of wish maybe there was a lock on the door, because who knows? Maybe we can keep that. What if the zombie apocalypse just started over there? You say don't worry. You got tools? Silly string, garlic, what is it? You got what?
You got it. Well,
I heard toothpicks.
no.
I was like, that's not going to do much for zombies.
No. I said I had 2 guns.
Oh.
No. But they're kind of like the smallest guns.
Alright. Are we good if the function's continuous at x equal to 0? Yeah. Okay. But now we've got to show that it's not differentiable. Now, we can think of our slope from our graph, right? That's pretty easy to do. It's not always so nice and easy, though. It could be some type of crazier function. So let's think of this as our piecewise function, just to kind of help us see how would we even do the derivative of a piecewise function. It's probably as easy as you think, but with one slight thing with it. All right, so we said that y is our absolute value. And we talked about that we can define, actually the definition of absolute value is that we have negative x and positive x. Negative x if x is less than 0, positive x if x is greater than 0. One of them needs to have an equals, it doesn't really matter. So this is how I define my absolute value function. This is actually how the absolute value is defined. So if I try to do my derivative, because have we learned what the derivative of the absolute value is? No. Oh, gee, you're about to find out. All right, well, my derivative for a piecewise function is simply taking the derivative of the individual pieces. But we have to consider the restrictions on the domain, okay? So what is the derivative of -1? What's the derivative of negative x? And we're keeping that same interval. And what's the derivative of x? 1. And we're almost keeping that same interval. We are not going to include the equal to part until we know that we can actually have that they're equal. Because sometimes with a piecewise function, the derivative might be the same on either side. But if they're not the same on either side, we don't have the derivative exists, and thus we can't have it even be defined. It's not part of my domain. It's not continuous. Alright, now this again also makes sense if we think of our graph. The slope on the left is -1. The slope on the right is +1. But again, that's a nice, easy function. Okay, so now in order for my derivative for my function be differentiable at that point, the slope from the left must equal the slope from the right. Right? Well, let's take a look. So again, we could write this with the different notation. We could use that as the limit as x approaches 0 from the left of y prime. Does that equal the limit as x approaches 0 from the right of y prime? Have you guys seen this notation before? A little question mark over equal sign? We're investigating. We don't know if it's true, that's what we're trying to find out. I think I actually saw it in gloss for one time in the textbook. Yes, that's right. Now again, that other notation we talked about, we could have said my slope coming from the left, does that equal my slope coming from the right? But we're doing this at 0, right? X equals 0. Again, if this was f of x, we said f of 0. I mean, really, we could probably just go and say y prime of 0 from the left, y prime of 0 from the right. It's not really in function notation. Alright, well, what's my slope from the left? What's my limit value? As I look at this piecewise function, what's my limit as we come from the left? -1. What's my limit as we approach 0 from the right? +1. Do they equal? No way, Jose. Alright, so again, even though this is a derivative, right, we're just doing the limit of a piecewise like we did before. We look to see what interval we look at. Okay? Again, same thing over here. Y prime from the left, -1, right? Y prime from the right was +1. Those are not equal. Alright, so this shows that my function is not differentiable at 0, which means we can't put the or equal to anywhere within there. Okay? The or equal to cannot be true. Alright. Can I squeeze in there? Yeah. Therefore, y is not differentiable at x equals 0. So therefore, y is not differentiable at x equals 0. Was that a lot of work? Yeah. Not too bad, though. We're just repeating, showing that continuity. We take a look at their piecewise, and then we take a look at our differentiability. Again, left-hand slope, right-hand slope. Alright, questions on that? Okay, let's do another one with piecewise. Here we're not actually going to do the show if it's continuous, show if it's not differentiable. But rather, plain plumb, here's piecewise, is it differentiable? Alright, which is what I want. Just a random side thought here. If I look at my function, on this interval, we agree that the slope is negative, right? What can you tell me about my function itself? Is it increasing, decreasing, or constant? Decreasing. On the right-hand side, my slope is positive. Is it increasing, decreasing, or constant? Increasing. We didn't draw a picture of our derivative. That's okay. Alright. Which that makes sense because if my slope is negative, that means my function's pointed like this, right? If my slope is positive, that makes sense. Increasing. It's got to have some type of positive notation like this, which means it is going up in some way, shape, or form, right? Does that make sense? We'll talk about that more later this unit. I think it's going to make those connections. I know it's something you could have reasoned for yourself. Alright. Let's let f of x equal a fairly innocent piecewise function, 2 minus x, and x squared minus 2x plus 2. That top piece is if x is less than or equal to 1. And that bottom piece is if x is greater than 1. Now, the question that we're going to look at, yeah, we'll just stick with the first part. is f differentiable? Is f differentiable? Where do you think we're questioning? Yeah. They could have asked you, is f differentiable everywhere, or find where f is not differentiable. Would it be differentiable along my top part of my equation? Yeah, polynomials are differentiable everywhere, right? We talked about that. Would it be differentiable everywhere for this chunk of my equation? It's an x squared. There's no restrictions there. We have it's differentiable there. So it's smooth and continuous differentiable for the first piece, smooth and continuous differentiable for the second piece. But where they connect up, is that going to have the same derivative from both sides? So you're going to have the same derivative, or maybe it looks like this, and thus it has that same derivative, or is it going to have different derivatives, where perhaps it does this. Oh, and then the derivative changes. Or maybe it looks like this. Okay, so we've got to investigate what is my derivative at that point. Okay, so we have our piecewise function. You know, it's probably good to check that continuity, because if it's not continuous immediately, it's not going to be differentiable at that point. And how do I know if a function, a piecewise function, is continuous at this point in question? What do I have to do? Yeah, just plug it into each piece, see if they're the same. So let's just do that real quick. 2 minus 1, what do we get? 1. 1 squared minus 2 plus 2, what do we get? 1. Okay, so we know it's at least continuous at that point. Bummer, we couldn't stop right there. Okay, now, is f differentiable x equal 1? Well, let's go ahead and take a look at what my derivative actually is. F prime of x. And again, you take the derivative of the individual pieces, leave the intervals alone, but don't put that or equal to until we know we actually have it. So what's the derivative of 2 minus x? Negative 1. And this is if x is, we're just going to say less than 1 for now. And what's my derivative of the second guy? 2x minus 2 if x is greater than 1. Okay, so what we need to know is it differentiable at 1? And if it is, then we can go and fill it in or equal to. Well, in order for it to be differentiable, the derivative from the left needs to be the same as the derivative from the right. So what is my derivative from the left of 1? Isn't this the left-hand part? So what's my derivative there? Negative 1. Let's see how this compares to my derivative from the right. If I take 1, put it in, what do I get?
Pardon the interruption. Warnings, we have some after-school announcements. Students, take action now. Darfur. Join us as we fight injustice and genocide in war-torn countries as we help those in need. Come take a stand with Stand in group 205 for the interest meeting after school. If you have any questions, see Ms. Costin. Do you want to perform at the homecoming bonfire? Well, if you sing, if you're in band, if you play an instrument, come audition Thursday, October 5th in the lecture hall right after school. Hope to see you there.
Okay, so my derivatives are not equal from either side. So is my function differentiable at 0? I mean at 1. No. Which means we cannot have that or equal to thrown in there, because it's not even defined at that point. It means my slope from the left is different than my slope coming from the right. So I cannot have it derivative. It's not a word. So therefore f of x is not differentiable at x equal to 1. Okay, your homework is worksheet 63. Remember, we did the quiz X class. Make sure you know your stuff inside and out. Right, isn't the quiz next class? Whatever the assignment sheet says. I think it's next class. When I'm done grading them, I'm still working on them. After your quiz, what'd you say? 3 takes. Thank you. Let me grab all that clothing, right? There's a student here whose last one was only 1. We're not related. I was really good at you. I think you're having experience. Oh, yeah. Yeah, so the so far you only have that limited kids, which often got to stay in your home. But once I get a test, yeah, I'm still working on the test.